Let's discuss the reflection and refraction of sound. We call the reflection of sound an echo. Most of us have experienced that sound nicely reflects from a rigid and smooth surface, like the plastic plates above the orchestra in this concert hall. In this concert hall, the reflective surfaces are large plastic discs. Sound, however, doesn't reflect from all surfaces. It's absorbed rather than reflected from soft and irregular surfaces like curtains or drapes. Here's Lil in an acoustical quiet room, where the spongy walls absorb rather than reflect sound. And why the thick covering of fuzzy scales on a moth that also are poor reflectors of sound? Ask a bat who hunts them by echolocation. Sound reflects from a smooth surface the same way that light does. The angle of incidence is equal to the angle of reflection. Note how sound reflects from the walls of this room. The angle of incident sound equals the angle of reflected sound. Sometimes when sound reflects from the walls, ceiling, and floor of a room, the reflecting surfaces are too reflective and the sound undergoes multiple reflections. Clap your hands in a large empty room and the sound persists after your clap. You hear reverberations. Reverberations account for the full sound you hear when you sing in the shower. If you sing in a room lined with drapes and where carpeting fills the floor, the reflective surfaces are absorbent and the sound level is low and maybe dull. Acoustical engineers strive for a balance of reflection and absorption in a concert hall. Let's take another look at the plastic plates above the orchestra in this concert hall. The reflective plates are large and shiny, and the reason is yum. Since both sound and light obey the same rules of physics, a listener can look up at these reflectors and see the reflected images of members in the orchestra. The plastic reflectors are somewhat curved, which increases the field of view. If a reflector is oriented so that you can see a particular musical instrument, rest assured that you will hear it also. Sound from the instrument will follow the line of sight to the reflector and then to you. Looking for an interesting career? Think acoustics. Sound does not always travel in straight-line paths. When sound travels in uneven winds or through air of uneven temperatures, it can bend. Here we see the bending of sound due to different air temperatures. Sound travels a bit faster in warm air near the ground than in cooler air above, so it bends away from the ground, as the large magenta arrow indicates. We say the sound undergoes refraction. The refraction of sound occurs when different parts of the wavefronts travel at different speeds. By wavefront is meant the front part of a wave, indicated by the blue lines, or green as I've indicated. The direction of sound is always at right angles to the wavefronts. The opposite occurs when air near the ground is cooler than air above. Then sound bends toward the ground. Again, the directions of sound waves are always at right angles to the wavefronts. As the wavefronts are bent, the direction of wave travel bends also. This bending away from the ground explains why you can often see flashes of distant lightning, but not hear the accompanying thunder. Sound moving slower, high in the air, compared with down below, bends the sound of thunder above and away from your ears. The refraction of sound occurs underwater, where the speed of sound varies with temperature. This poses a problem for surface vessels that bounce sound waves off the bottom of the ocean to chart the sea bottom's features. Refraction is a blessing to submarines that wish to escape detection. Because of thermal gradients and layers of water at different temperatures, the refraction of sound leaves gaps or blind spots in the water. This is where submarines hide. Ultrasound images of preborns is accomplished with multiple reflections and refractions of ultrasonic waves. The high frequencies of ultrasound are beyond the range of human hearing. Waves of ultrasound entering the body are reflected more strongly from the outside of an organ than from its interior. This enables an image of the outline of the organ. Ultrasound is old stuff to creatures such as bats and dolphins. Bats emit ultrasonic squeaks and locate objects by their echoes. Dolphins do this and more. Whereas sound is a passive sense for us, it's an active sense for the dolphin, who sends out sounds and then perceives its surroundings on the basis of their echoes. Sensing ultrasonic waves enables the dolphin to see through the bodies of other animals and people. Skin, muscle, and fat are almost transparent to dolphins, so they see only a thin outline of the body. But the bones, teeth, and gas-filled cavities are clearly apparent. Physical evidence of cancers, tumors, heart attacks, and even emotional states can be perceived by the dolphin, as humans have only recently been able to accomplish with ultrasound. We'll see in future lessons that reflection and refraction occur for light waves and waves in general. So what causes refraction? The answer is differences in wave speed. I want to leave you with a question. First, have you ever been in a location that favors hearing your echo? Like in a large empty warehouse or a valley surrounded by steep surfaces? Here's my question. Suppose you're in Echo Valley and shout, "Yum physics!" and hear the echo 4 seconds later. For sound traveling at 340 meters per second, is the reflecting surface more or less than 1 kilometer away from you? Until next time, good energy.